All right, section 5, chapter 5, section 1, probability. What we're going to do in this section is we're going to look at the probability distribution. We looked at frequency distribution earlier in the chapter, in the course. And we created a histogram based on the frequency polygon. But now we're going to look at creating with a histogram using probability distributions. And note, with probabilities distributions, we can find the mean, variance, deviation. We can find all that stuff with probabilities as well. It actually makes it easier sometimes. And then we're going to determine what's significantly high, significantly low, so we see what's valid, what's not valid. So the first thing we got to do is define or do our two definitions. We have the first one we have are random variables. This is your X value. A random variable has a numerical value that is determined by chance. That's a procedure that we do in our whatever our probability experiment is. We're going to, whatever it is, like picking a card from a deck of cards or rolling a die. That's each event has a value determined strictly by chance. The next thing we're going to define is the probability distribution. The probability distribution is the probability of each value of the random variables to be determined. So the probability distribution is the chance of each of these random variables to be selected or calculated. We have two more definitions. A discrete random variable it's a collection of values, I should say, not variables, that are countable. What countable means is it has an end. It doesn't go to infinity. We can count up to 1,000. We can count to 1,000,000 even, but we can't count to infinity. So a discrete random variable is a collection of values that of our random variables that are countable. Then the other side.
Sorry, Professor, to disturb you. You sent in 1314, not 1342.
Excuse me?
You sent in Maths 1314.
Oh, okay. So at the end of class, remind me at the end of class because or when I take a break, I'll send it. Then we look at continuous random variables. As opposed to discrete random variables, which are countable, which are finite, these are infinite. finitely many values. In other words, they're not countable. So we have, okay, random variable is a numerical value that's determined by chance of each event that we do. The probability distribution is the probability of each value of each of the random values being determined. It's a complete list of all of them. The discrete random variable is a collection of values that are countable, and continuous are the collection of values that are infinite in value. The properties of a probability distribution. And we have two or three of them, actually. The first one is the summation of all the probabilities has to equal 1. Remember, 1 is decimal, 1.0, which correlates to 100%. Okay, because of something called round-off error, whenever we deal with fractions, if you get a number that's like 0.999999, that's good enough. Or you get something 1.001 or something like that, very distant decimal points, those will be close enough because of round-off error. The second one, each probability has to be between 0 and 1. These are the big ones. The sum of all your probabilities has to equal 1, and each individual probability has to be between 0 and 1, cannot be greater than 1. And that third one actually defines all of those already we just talked about. So let's look at an example here. Now, let me. All right, let's look at example 1. We'll get male and female births are equally likely to occur. So what's the question here? Let's consider 2 births from the following random variable. Okay. That X equals the number of females when 2 babies are born. So what are the let's look at each of these probabilities. What are the possibilities that we can look at here? We have two babies are born. What is the probability of females being born? Half? No. We can have no babies are born that are female, nor is they're both boys. We have one female born. That's girl and a boy, or boy and a girl, or they're both girls. So what are the probabilities of these? The probability of 0, 1, and 2. So what's the probability of no girls being born?
Boy,
Of two
boy.
births. So what's the probability? So we have a probability of a boy times the probability of a boy.
Boy.
And they're both equally likely, so they're both 1/2. So that's 1/4. Now the probability that one girl is born. So out of these two chances, what's the probability of the girls being born?
1.
1/2.
Mhm.
Because out of the two babies, one of them is a girl, so it's half.
Mhm.
And the probability that both are girls, they're both 1/2, so it equals 1/4. This is 0.25, 0.5, 0.25. So this is where we check. Do they satisfy our conditions? Each of these probabilities, are they between 0 and 1? Yeah, they're all decimals.
Mhm. Yes.
So that's check 1. If we add them together, does it equal 1?
Yes.
Yeah. 0.25 plus 0.25 is 0.5.
5.
0.5
5.
plus 0.5 is 1.0. So check those. That is a legitimate, valid probability distribution. From this information, we create a histogram. What's a histogram? What does a histogram look like? What's the difference between a
Histogram.
histogram and a bar chart? They touched. So
Like a
we
bar
have
chart, but they touch each other.
the histogram touches, yeah. And for this one, we have 0, 0, 1, 2 outcomes possible. We have 0.1, 0.2, 0.3, 0.4,
0.5.
0.5. And then we go 0.6 if we want to, 0.6. So this is our probabilities, and these are our number of females born, or girls born. So the chance of getting 0 was 0.25. So we put a box that goes, well, it has 0 in the middle of that box on the bottom, and it goes up to 0.25. The 1, that one goes up to 0.5. Remember, it connects to the box on the left, and the denominator, I mean, not denominator, but the x-axis is located in the middle of the box. And the last one is also 0.25. So there's our histogram. We have 2 boxes that go up to 0.25 on both ends, and the middle goes up to 0.5. This is why it's called a probability histogram. Why is it called a probability histogram, ladies and gentlemen?
Because it overlaps.
No. Look at the vertical axis represents the probability, the percent chance. So that's why. If it was integers like we did earlier in the course in first chapter or chapter 2, then it would be just a histogram. Because that would be a frequency histogram because it's looking at the frequencies of numbers. This one looks specifically at the probabilities. Okay, let's look at formulas now, because we're going to start dealing with equations in a minute. The probability formula. So the formula we're looking at here, which we're going to look at in a little bit, we're going to look at permutations and combinations. And because of that, we're going to be using factorials. And factorials are denoted by an exclamation point. That's a factorial. So the probability formula could be denoted as 1 over x factorial n minus x factorial. And again, I'll go through these in a second, what they mean. We're getting to those. We're getting to those. Let's take an example 2 real quick. Example 2 says the table below, which I'll read out in a second, lists countries along with the proportion of unlicensed softwares in each country. Does the table describe a probability distribution? Okay, the table looks like this. There are 2 columns. The first column is the country, and the second column is the proportion of unlicensed software. In other words, they're pirated. The first country is the US. Its proportion is 0.17. Then comes China at 0.70. Then India at 0.58. Russia at 0.64. Actually, that's 4 of them. 1, 2, 3, 4. Yeah. So what it's saying here, the table represents the proportion of each country, inside each country, how much percent of the software in that country is unlicensed. So if we change these to percent, it'd be 17% of the software in the United States is unlicensed, 70% of the software in China is unlicensed, 58% in India, and 64% in Russia are unlicensed. So the question is asking, does this table represent a probability distribution? Remember, to be a probability distribution, we have to satisfy 2 conditions. First condition, are each of the probabilities between 0 and 1? Yeah, they're all 0 point something. So check. The second condition, if we add them all up, all the probabilities, does it equal 1.0? No, because 0.7 and 0.5 is already bigger than 1. So that's where it fails. So it's not a probability distribution. So, and here's another important part. When we talk about probability distributions, we don't talk about samples, we talk about the population. That's why an entire country, United States, China, India, Russia. So it's the population of all of the samples that are being used. And because it's population, our values are going to be more accurate than if they were just of samples. So because of that, we can now use these values, these probability distributions and values, to figure out the mean, variance, and deviation. Remember last chapter, we dealt with the formula for, remember the deviation was x minus x bar over n. So let's look at how these are going to work. Here's our first formula. The mean value. Since we're dealing with a population, we have to use the Greek letters. Remember, if we use our alphabetic letters, that represents a sample. If we use Greek letters, then that represents the population. So the mean variable is the mu. It's the Greek U symbol, like a cursive U. These are all for probability distributions. So yeah, if you're gonna get a cursive U with a long left side. So the formula for the mean is the summation of each individual outcome times the probability of that outcome. We have to look at the absolute value of it because our outcomes can be negative. And if we have negatives, then we come up with 0, which means that it's an impossibility. It'll never exist. So that's where we take the absolute value of it. The second, the variance. The variance is rho squared. Rho is that O with a loopy thing on top. This is mu, mu, and this is rho, R-H-O. Like fish eggs, rho. So rho squared, the variance, is equal to the summation of the individual x values minus the mean squared times the probability of that outcome. So it's x minus mu, the individual value you have, the answer you have, minus the mu, the population mean, squared. When you square it, that gets rid of the negatives. The probabilities can never be negative. Remember, they have to be between 0 and 1. So the only way it could be negative is if the value is to the left of the mean. When we square it, we get rid of the negatives, which is why it's rho squared. Now, there's a second form of that rho squared. It's summation of x squared times the probability of x minus the mean. So what we're doing here, we can take the x squared, square your value, times the probability, add up all of those and then subtract that from the mean. Squared. Deviation is simply the variance, the square root of the variance, which is just rho. So the way we could do is you either find the deviation first and then square it, you get the variance. Or if you find the variance, you can take the square root of it and that'll find the deviation. So the rho equals the square root of x squared times p of x, all that summed, minus mu squared. So you can take either one of those two equations that you have earlier and square root it. Typically, for the variance and deviation, because the more decimals we have, the more difficult it becomes to contain. So that's why we usually limit it to one decimal place. So round it to one decimal place usually. Expected value. We talked about last time, the probability of rolling a 3 is with roll of a die is 1/6. So what that would mean that is if you roll it 6 times, you'll get a 3 at least once. Or if you only roll a 6, you can get no 3s. It's just that because of the laws of large numbers, you have to do it many times. And that, as it turns out, is it becomes a ratio of 1 out of every 6 rolls. Then you get the value you're looking for. So the expected value, the definition of it, the expected value of a discrete random variable is E and is defined by the formula E is equal to the summation of x times p of x. That's the expected value of your mean. Because remember the formula, x times p of x, what that really represents is your average, your mean. So let's look at example 3. Let's look at our expected value. Find the mean, variance, and deviation for the example we had earlier, the 2 births and looking for females. Two births and the number of girls. So what do we have to do first with this? To find the mean, variance, and deviation, it's much easier if we use tables. In the first column, we'll have our possible outcomes. Remember, we have only 2 births, we're looking at number of girls. And those possibilities are 0, 1, and 2. Let's look at now we have to find the probabilities of each of those occurring. So the probability of 0 births being done is 1/4 or 0.25. The probability of 1 girl out of 2 births, 1/2 or 0.5. And then the probability of 2 girls being born, 1/4. So it's back to 0.25. To build our table, we have to look at what the formulas we're dealing with. The formula for the mean is the summation of x times p of x. So we have to add up. So the first thing we have to do is multiply x times p of x, and then add them all up. So we have x, our third column is going to be x times p of x. So 0 times 0.25 is 0, 0.0. 1 times 0.5 is 0.5. And 2 times 0.25
0.5.
is 0.5. Add them up, you get 1.0. And that is your mean. Does that make sense?
Yes.
Because what I was telling you, the average is 1 girl out of 2. Because this only happens once. The no girls happens only once. The 2 girls only happens once, but the 1 girl can happen 2 ways. It could be the first birth, then a boy, then this, or it could be boy, then the next birth is a girl. So more times it happens, you get 1 girl. So that's the mean. Look at the variance formula, which we had, that was the x minus mu squared times p of x. Because we have the mu, we have the x's, and we have the p of x's. So now we have to create that column. We have to create x minus mu. We're going to build it slowly. So the mu is 1.0. So 0 minus 1 is
1.
negative 1.
It's a 1.
1 minus 1, 0. 2 minus 1,
1.
1. Okay, so that's the inside there. Now we got to square those. So the x minus mu squared. Negative 1 squared is
1.
0 squared is 0. 1 squared is 1. So we just built this part. Now we have to multiply each of those by the probability. So we have the x minus mu squared. Now we got to multiply by p of x. So 0.25 times 1 is 0.25. 0.5 times 0 is 0.0. 0.25 times 1 is 0.25. Now, according to our formula, we have to add up all those. 0.25 plus 0 plus 0.25 is 0.50. So our variance is 0.5. That's rho squared. That's our variance. This is our mean at 1.0. How do we find our deviation? Deviation is simply the square root of your variance. So we get the square root of 0.5. Whatever that is, that's your deviation. Make sense? I mean, it's all step by step by step. It's the way you read how to do the formulas. That's how you build your columns. So what is the square root of 0.5? What is it? 0.7. It's has more decimals, but it's probably repeating. It's 0.7. He goes on 0.707s. So that's how you find the mean, median, and mode, or mean, variance, and deviation. I'm sorry.
0.7.
How do we determine if it's significantly high or significantly low? Or insignificant? Right, we use that 2 deviation rule. We call this the significant results with the range rule of thumb. So the range rule of thumb helps us to identify significance of values. We have significantly low values, and that is mu minus 2 rho. Or in English, the population mean minus 2 population standard deviations. It's the same as it was last time. Remember, it was plus mean plus the deviation is significantly high. The mean minus 2 standard deviations is significantly low. Anything in the middle is not significant at all. So significantly high values represents by mu, or the mean, plus 2 standard deviations. It's to the right of the mean. Values that are not significant, anything between mean minus 2 standard deviations and mean plus 2 standard deviations. Anything between there. Again, it's nothing new because we did that same thing last time. Example 4. Identify significant results with the range rule of thumb. In example 3, we found the 2 births, the mean value, the mean was 1.0 and the standard deviation was 0.7. Using those numbers and the range rule of thumb, determine if 2 females in 2 births is significantly high. Determine if 2 females in 2 births is significantly high. How do we do that? Since we're looking for high, then we have to go mu plus 2 standard deviations. So it's 1.0 plus 2 times 0.7. Excellent, excellent. So 2 times 0.7 is 1.4. 1 plus 1.4 is 2.4. So any number higher than 2.4 is a significantly high value. Actually, anything 2.4 or higher, I should say. Anything less than 2.4 is insignificantly.
So we're saying 2.4 is in the middle.
Well, no, the mean's in the middle. Because what we're
Okay.
looking for is
Yeah.
this, is we have the mean, then we have minus 2 standard deviations, and we have 2 plus standard deviations. So if the mean is 1.0, then we have
Right is high.
2.5, that's high.
Mhm.
And then 1.0 minus 1.4, you can't have negative, so we're down to 0.
0.4.
So anything below 0 is negative,
Below
because it
1.
would be negative point. It'd be negative 0.4 on this side, which you can't have. So it would say that anything lower than negative 0.4
4.
would be significantly low.
Low.
Significantly high number of successes. What do we mean by successes? Yeah, success is whatever you're looking for. It's not always a good answer. It could be what you're looking for is the number of car accidents. So the success is if there's a car accident, which is not good, but that's what you're examining. So that'd be your success. What you're looking for here, significantly high probabilities of success would be is if the probability of X or more events is less than or equal to 0.05. Or the other end, X or fewer events. This is for significantly low. As long as that probability is less than 0.05. Typically, we use 0.05 as the level of significance that we're looking at. Because what it tells us is, if we look at the bell curve, we're looking at 0.05% of the data is higher than your +2 standard deviations or lower than -2 standard deviations from your mean. So that's what you're looking for, is the probability of that falling back there. Right? Now let's look at something called the rare event rule. The rare event rule for inferential statistics. First off, I have to ask you, what does inferential statistics mean? What's an inference? Not really an assumption. Assumption is a guess. This, when you infer something, you're saying, from what I've noticed, this is what is happening. It's a uncalculated opinion based on your observations. You're inferring this is true. So this is the rare event rule. If under a given assumption, remember I just said, it's an assumption, it's not calculated. If under the probability of a particular outcome is very small, and the outcome occurs significantly less than or significantly greater than what was expected during that with our assumption, then we can conclude that the assumption is probably incorrect or wrong. If under a given assumption, the probability of a particular outcome is very small and the outcome occurs significantly less or significantly greater than what we expected, our assumption, then we conclude that our assumption is probably wrong. What does that mean in English? Because again, think of the two parts the same. If under a given assumption, the probability of a particular event, the probability of an event is very small, and the outcome that occurs is significantly less or significantly greater than what was expected. Think what that
It means
says.
that we are wrong. It means the answer is wrong.
Right, because now it's just putting us in the middle. So it says our assumption is incorrect. Because again, it's a rare event. It doesn't happen all the time. There is an example here. Example 5. Identifying significant results with probabilities. Here's a statement. Is 252 heads in 460 coin flips a significantly high
Oh no.
number of heads? So what do you think? What would you expect to happen, first off? If you had 460 coin flips, how many heads do you think would be in there? Yeah, you guess half, because each side has an equal number of chances to come out. So half of 460 is 230.
230
So this number
is high.
is higher than what we expect by any random event. So what does that mean?
It's significantly high.
It's significantly higher, yeah. Because it's well out of our guesstimation. Because we guessed 230, it came at 252. That's 22 numbers higher. That's
Yeah.
a good chunk. So yeah, it's a significantly high chance. Expected values and formulas. Ooh, good, more formulas. Example 6. Be a better. Be a better. What that means is be a better gambler. You place $5 on a bet at the Golden Nugget Casino in Las Vegas. You have narrowed your choice in one of two bets. Okay, so you have a $5 bet. We have two games. The first game is roulette. The second game is craps. If you've never gambled, good, don't do it. It's a very nasty habit. I love it. I go to Vegas whenever I can. Each one of these two games have their own odds of winning. Roulette is that wheel. It's broken up into a whole bunch of these very small pieces. There are 36 black and red spaces, 18 of each. 18 blacks, 18 reds. So on the main board, you have 1 through 36. On the very top of the board, here's how you have, this is how it looks when you bet. You have 4 columns, 9 rows, 36 of them in there. And then in the very top, you have 2 green ones, a 0 and a double 0. It used to be that those zeros didn't exist. The casino didn't like that because over here, you can have one of two types of bets. You can go 1 through 18, 19 through whatever. It separates them into three areas, 1 through 12, or 1 through 11, 12 through 23, and 24 through 36. You can bet on each one of those. Those are 3-1. What does that mean? If you bet $1, you can get 3 back, because there's 3 possibilities. And then you can have either black or red. These are 2-1. If you bet $1, you can get 2. You can get your initial bet back plus another $1. So the casinos thought, hey, that's I'm losing too much money here. So that's why they put the zeros. It used to be 1 green 0. They weren't winning that much. Then they put 2. That put the odds in the house favor. So let's look at this. With the roulette, you bet $5. And we should put in there. You bet on 7. 1, 2, 3, 4, 5, 6, 7. You put your money here on number 7. If you get this number here correctly, you have a 35-1 chance. So your $1 bet will give you $35. So let's build a table here.
So each one of the space is $5.
Well, no, each one of these spaces inside here are numbers. You can put as much money as you want to, as long as your total bet is, let's say, $5 or more. So if you're going to bet on one of these numbers by themselves, you can put either $5 on one number, or you can put $1 on 5 different numbers. So as long as your minimum bet is at least $5, they give you $1 chips. So if we look at this thing, with our bet, this is what our event is going to be, our X. We can either win or lose. Now, if your bet, if you win, how much money would you win? You bet $5 and it's 35-1 if you win. So 35 times 5 is 175. If you win, you get 175. If you lose, you get a -5 because you lost your bet. So what's the probability? The P of X. What's the probability of winning? Remember, you have 36 numbers and there's 2 greens.
1/35.
1/38. Because remember, you have 36 numbers on the bottom, and then you have those 2 greens. So 36 plus 2 is 38. Only one of them wins. How many of them lose?
1/5.
If 1 out of 38 win, that means 37/38 loses. So now we multiply those together. So X times P of X. So the probability of winning, 175 divided by 38, you would win $4.61. The chance of losing, it's going to be a negative, is 5 times 37/8, which is negative
38.
4.87, which is 37/38 times 5, which is 4.87. Now, if we add up all your x times p of x, so it's negative 4 point, the answer is going to be negative 4.87 minus 4.61 would be 0.26. So you would lose every round. You're guaranteed to lose 26 cents every spin of the roulette table. Because the expected value, the x times p of x is the expected value. That's the expected value of winning as opposed to the expected value of losing. So in other words, every roll, you're guaranteed a losing bet. That's roulette. Now, craps. Craps is a little bit better for you because now you have a little bit more control of what happens. Craps is when you roll 2 dice and you get to pick whether it's going to be on a certain set of numbers. The table pretty much looks like this. You have the betting numbers here, which are 7, 8, 9, 10, and 7, 6. Not you can't. There's no 7. 5, 4. These pay, I think, 7 to 1. And there's a whole bunch of other stuff. You can bet whether it's gonna, if you, on the first roll, it's called a come out roll. If you get a 7 or 11, you win. But if you don't, whatever number you roll, that becomes your point. Let's say you roll a 9. They'll put a marker there on the 9. What you're betting now in craps is that you're gonna roll another 9 before you roll a 7. Now, why is that a losing hand? Because the 7 with 2 die happens more than anything else. It happens 1 out of 6 times. Everything else is a lot lower than that. And actually, after we finish this section, we'll go ahead and I'll show you the probability with 2 dice being tossed. So with $5 bet, you bet on the pass line. What the pass line is on the first roll, you're betting that the person's going to roll a 7 or 11. So $5 on the pass line. Remember, we're looking for the expected value. So we have to create another table here. The event, the X, the probability, and X times the probability. So we're going to look at here is we're going to lose and win. So if you lose, you're out $5. If you win, you get your $5 back. Because all you did was bet whether it's going to be a 7 or not. It's not too difficult. But the probabilities of what goes on here is a lot more. There are a total of 495 bets that can occur on a craps table. There are 251 of them that says that you're going to lose. 244 of those are going to say that you win. Now, if we multiply the -5 times 251 over 495, we get negative 2.54. And to win, take our $5 bet times 244 times 295. It's going to be a positive $2.48. Add up find the expected value, or add up the x times p of x, which is negative 254 plus positive 248.
Where do you get 248?
Multiply these two, x times p of x, this times this.
Okay.
So it's going to be minus. So it's 0.14 So what this thing says is you're guaranteed to losing, this would be negative since that was bigger. You lose 6 cents every time somebody rolls a die. So which game is better for you?
It's 246. It's 2.46.
This
Not
is one
4.
of the 3 games in casinos where you pretty much have the closest to the house. 6 cents a roll, you can play for hours on that. But roulette, pretty quick. The next ones are blackjack and baccarat. Those are the ones that you could win. All right, well, that's it for that section. So I'm now converting you guys into casino people. Actually, the thing is, if you play to win, you'll lose. If you play to have fun and not make any big exorbitant bets, you'll play for a long time.